It is we are humbled and honored to be in this school, to be with the name of Abdus Salam, which this school carries as a trademark or logo proudly. I'm grateful to my friend who set this ASMS up, who is no longer with us now, and who is running it at the moment. And this is meant to be an introduction to some topics which are not too difficult. It was meant to be this, but now we need to assess. So it has become a course as well. So that there will be assessment, and in my opinion, there will be one exam, closed exam, and another report or project. Then it will be distributed percentages like 20/80 or 30/70. Would that be acceptable? And this applies to only those who would like to obtain a certificate. This is not credited, but it's a certificate given to you. If you are happy about what I just said, we will carry this out. Is that okay? And then I would like to ask my colleagues, Dr. Haimuddin and Dr. Ali Raza, to watch out for me. I'm old, I'm retired. Every mistake I make will be your responsibility. And every correction you need to make. And if I'm stuck, you continue. Okay? Or any one of you. So this is a research introduction. My topics are easy, which is, I'm not saying it, it's someone else actually said it. I told Hamza yesterday. When I submit this paper in this topic, it is usually accepted immediately within 10 days. But with an email from the managing editor saying that it's easy. What do you think if your paper is accepted and the managing editor said it's easy? What do you feel? Some people feel offended because easy things are not usually published nowadays. It has to be hard first of all. But I was very happy because at last I found someone who understood the paper. For those papers which are not easy, the referees and the managing editors probably don't understand it, and the author don't understand it. Now what is the meaning of that to do mathematics if you don't understand that? So this is the whole topic is called geometric sets in metric spaces. One thing I have, another political statement. You are most welcome to use your phone to take pictures and record. In case, when I was planning, in case it is not on the slide, it is on the board, you should take a shot because some wording will be on the board who may not be in the slide. So you are not, I'm not offended. You take pictures or record, no problem. This is the topic which I chose after Professor Ram Shabi requested that I should give a mini course, which I didn't know what it was. So the main word is metric spaces. And we are going to thoroughly do it. I have a completely prepared slides for everything, except some words which I will do on the board. Main word is metric spaces in its most generality. And the things we are considering are geometric sets. What are geometric sets? What geometric sets in the Euclidean spaces you can think about it? This question, try to answer quickly. what geometric sets do you know in the Euclidean plane, for example, or in Euclidean 3 space, or any Euclidean spaces? What geometric sets we have studied in beginning undergraduate? Just one word will be appreciated. Anybody knows what a circle is?
Yes, circles.
Unit circle is one of them. And ellipses,
Yes,
parabola, hyperbola. We were studied rigorously in analytic geometry and in synthetic geometry. There are other geometric sets, such as in the Euclidean plane, Euclid himself. If you give 2 points, suppose that this is Euclidean plane. This is not Euclidean plane, but you have 2 points, A and B. They don't have to be 2, but let us assume it's 2. Then Euclid actually constructed the bisector of the line segment A, right? Using compass and ruler. Compass and ruler. So the tools are compass and ruler. The Euclidean compass is a compass which can measure any distance and reproduce it. Any finite distance and reproduce it. Euclidean ruler is it's called a straight edge. It's a straight edge without markings. So you don't use the marking one. The ruler which is shown in the marking. I thought this was a ruler. So the straight edge is just something like that. There's no markings. How does he do it? I really want to, anybody have a shoelace? You put your compass here and try to estimate that it should not be shorter than that, or shorter than the half of it. And then you do a little arc there, and you do the same, another little arc there, and then this side you do the same, and then you determine 2 points. Through those 2 points, by the second axiom, there is a unique straight line going through. That straight line has the property that every point on this straight line has equidistance to those 2 points. So that straight line is one example of a geometric set. Of course, any straight line is an example of a geometric set. So these are the ones we are going to discuss. But before, as I promised in my announcement, we start with unit circle, and we're going to get there right now. So let's start with unit circle, and everybody you should be really proud to say that you know everything about unit circle. And whenever I ask you a question, you need to answer immediately. Okay. But before we do unit circle, we look at the trigonometric function values on special angles. The school teachers taught us a table even. So the table contains sine, cosine, tan, cotangent, sec, cosec. 6 rows with something like at least 6 columns. Let us, because if we have already proved the trigonometric identities, then we only need one of the trigonometric functions. But nevertheless, I'm going to include 2 of them. So the cosine and sine. And t is my angle, and which is a real number, meaning that we are not using degrees. A degree is not a real number, we have to know. This is radian angles. In order to measure, why do we need, this is another teasing question for young students. Why do we prefer radian angles to degree angles? Quick answer. We want to compare x with fx. They have to be they have to be in the same field, real numbers. We want to compare sine x with x itself. If we have degree there, sine x is a real number, this is the degree, so you can't compare. That is the only reason we, and which is the solid reason we need real numbers. This is actually very fast if you display it over there, but it's fine. Oh, I see. The top one must be longer, wider. No, these are magnetic. We only consider angles from 0 to half pi. with the trigonometric definition, function definition, and these identities, you can use something called complementary or angles to go to half pi to pi, and then you reflect to the negative y-axis. So we look at 0, start with 0, 0. We start with 0. It is not coming. She is refusing to come help me. So this is 0 angle. Cosine 0 is 1. Sine 0 is 0. And then we come to the next. Of course, you can put any number of real numbers. Say if you wish, using the half angle formula, you can put anything which is divisible by t over 2 to the n. For any natural number, and you can do. And then next one, usually we come to pi over 6 or 30 degrees. And then cosine is root 3 over 2, right? If you still remember the school thing, and this is half.
Yes.
And then we have pi over 4. Both of them are root 2 over 2 or just 1 over root 2. It's not coming. And pi over 3. These two are reversed. This is what I'm saying, you need only one of them. And so on. Only half pi will do it. Half pi will reverse these two. This is a school teacher's trigonometric function value for special angles. And some Pakistani teacher uses a rod to force you to memorize. But if you know the definition of cosine, you know everything because you don't need to memorize. If you know the definition of cosine or just sine, it's all there. Now, this is not an important thing. The important thing is, let me ask you a question, and you need to answer quickly, as quickly as possible. For which of these special angles both cosine value and sine value are rational numbers? Quickly. Which? Only these two, right?
0. Pi by 2.
Both of them are rational numbers, only those two. And even if you look at from 0 to 2 pi, there you can find only 4 points, the intersection of the unit circle with the coordinate axis where you have rational numbers. And anywhere else, have you ever seen any rational number, any point, any angle t for which both cosine and sine are rational numbers? Quickly answer.
Multiple of pi by 2.
Pardon?
Multiple of pi by 2.
Multiple of pi, yes. Of course, but they are still, because of periodic function, they are still one of those 4.
Yes.
One of those 4 points. 0, half pi, and 2/3, 3/4 of a pi, and 2 pi. Any other point, school teacher or you actually wrote down when you were in school, or even in university? That is what we're going to start this whole course with. This is where we start. Any point, other point you can have. I was looking for, but there are lots of nice pictures which I have in the slides.
Just 5 more percent left.
Eh?
It started updating.
Yeah, that's fine. But now we do something which we can write on the board. So let us, for any real number t, any real number t, let x be equal to cosine t and y be equal to sine t. Then by the trigonometric identity, we have x squared y squared plus x squared y squared is 1. Right? That is where we said unit circle. This is unit circle.
Yes, yes.
This is unit circle.
Okay.
In the Cartesian coordinate system, which I have lots of jokes about this in my slides. So what the 4 points we discussed was these four. 4 points we discussed was these four. And there are two pictures which will lead to what they are nice pictures. In one of the pictures, it was they are both from ancient Greek time. 3 people were just stretching a rope with knots tied on it. Each 2 knots have the same distance away from each other. It has been like 4-1. And then one side is 4. One of the side is 3, the other side is 5. So meaning that if you figure out this x squared plus y squared is r squared, let us say, then if you substitute 4 for x and y, satisfies the equation for r equal to 5. Three squared, 4 plus 4 squared is 5 squared. That was Pythagoras' time.
Yes.
300, maybe 900 BC. So what does it mean? It means 3 squared plus 4 squared is 5 squared. All elementary mathematics. Now you divide this both sides by 5 because 5 is non-zero. If it is 0, you can't divide. Lots of Facebook, lots of internet things they divide by 0. Nowadays they put out this fake information. But before you divide, you have to know, make sure that the number you are dividing is non-zero in Z. 5 is not 0. Therefore, 3 over 5 squared plus 4 over 5 squared is 1. Therefore, if x is equal to 3 over 5, y is equal to 4 over 5, then this equation is satisfied. Which means cosine can be 3 over 5, sine can be 4 over 5, for which there is an angle definitely, but we didn't even, there exists an angle so that both of these are rational numbers. Clean and nice rational numbers. Yes, go to N Lahore. N Lahore, N/Lahore. N/Lahore. Then we continue N/Lahore and then go to NEC and then display LA.pdf. Now, this gives us one angle for which both cosine and sine are nice rational numbers. And if you N-Lahore, and if you multiply top and bottom by 10, for example, let us just write this here. It's still the same, isn't it?
Is it this one?
LEC, the second one. Open it and then there's an LA, not L1, LA. Down. Because numbers come first, that one open, full screen. So I wanted to display the actual course. This is just an appetizer. Actual course thing first, because I'm not this kind of code. So only this full screen. You're not using an upload. Okay. So does it show that out? Okay. So that is what we were just talking about. Yeah. You can continue. That one I don't trust it too much. The keyboard is dead. Continue. So we have set that already. Why is keyboard not working? Maybe we should join my computer. Then it will be all great. Also, the right side of the text is all outside the screen. Maybe you should point to this. Okay, so this means that I found we can find now infinitely many angles between even between 0 and half pi, for which both cosine and sine sine values are rational. Even in this on this arc. You don't have Adobe Acrobat? There are infinitely many angles. No, sorry, this one. I'm very speedy sometimes. This is why I'm asking you to not this, it's this one. It doesn't matter which. It will be about the same. Even on this arc, there are infinitely many rational points whose both coordinates are rational numbers.
Yes.
And this question was asked by a young schoolboy in a secondary school in 1976 with his mathematics teacher. And the teacher liked him very much, so he kept this memory until he was old man. This question said that which of the cosine, for which angles, cosine value and sine value are, because he didn't know what rational number was, but he said ratio of two integers. This is going to stick to the end of the course. So it's working out. So we have passed this already. Now we look at the argument over here, which is with pictures. Everybody recognizes this if you write down x squared plus y squared r squared, or 1. Nowadays, young people, and they don't know the original geometric definition given by Euclid. And this means that we are going to visit Pythagoras. His name is not Pythagoras, English people pronounce it wrongly. His name is Pythagoras, this guy. Of course, there was no photograph by that time, no camera. Some people imagined he was and drew him. Pythagoras of southern Italy, called Greece. So 3 people using a rope with knots on it. Between every consecutive knots, the distance is the same, which we may assume 1. And then you can actually fix at the 3, 4, 5. That means that that is how the right angle was measured in engineering during Greek time. So that gives us this idea. And we know that there are infinitely many Pythagorean couples or triples. Therefore, we have infinitely many rational points on the unit circle. What's happening? Okay, so the question number 1. This is the wrong file. The question number 1 is determine rational points on the unit circle. And we keep the unit circle precisely. Yes. Equal to geometric set x, y, R2, such that x squared plus y squared is 1. My PhD student and I have a recent paper which we just submitted. We proved on that using very elementary proof that all the rational points on this circle, namely what we proved was S intersect Q squared is density Q squared, or density S. This one I was saying. Are you understanding? Another thing I wanted to say in the beginning was you should stop me as soon as you feel, even at this elementary level, as soon as you feel you cannot convince yourself, or I didn't convince yourself, you need to stop me and discuss. This is meant to be a discussion session throughout. But it has now become a course, and I really don't like lectures. The lecturer always talk here and nobody else cares about it. That is not good, because in mathematics you need to have it as your own. It's your thing, not just this guy who is talking. So we proved that this set is dense. Of course, that is a subset of S. It is dense. It is dense, but it cannot exceed the cardinality of the natural numbers, because this cardinality of this set is equal to the cardinality of natural numbers.
Yes.
We know that. So it cannot exceed that. So we hit, it is dense and we hit the first infinity cardinality only. So that is one thing here. Now, let me tease you further, because now you just replace this equation by x squared plus y squared is equal to 2. Will the same conclusion come out?
Yes.
Someone said yes? Should give me a quick proof of that. Now, if this right-hand side is replaced by 3, what happens? Or any rational or real number, positive real number. I was making mistakes when I was doing this thing. I was thinking that all circles would be fine, because you have a bijective mapping between them, and the geometric property should be preserved. For example, the S intersect Q squared is dense. This is a geometric property because it's a topological property, which should be preserved by homomorphisms. Bijective mapping both its inverse is also continuous. Bijective continuous mapping inverse is also continuous. But you should really try at least to do these two, and you will find new truth. I'm not going to reveal this new truth now. So we are now going, this has stopped here, we'll go to the real lecture. Go to L1. Before going to L1, we not only proved this, we proved for any Sn. So S is definition of Sn. N-dimensional sphere is a subset of the n plus 1-dimensional Euclidean space. Such that there is some